one. I need the row for 30 degrees, sine, cosine, and tangent value. Madison, will you get us started, please? Uh-huh. Good. All right, Troy, can you do 45 for me? Good. Michael, 60 degrees. Sine of 60.
Square root of 3.
It is. Cosine of 60? It is, Adam. You're right. Cosine is 60 degrees. We'll come back to you, Troy, or Tommy. Sorry. Yes. And keep his tangent for me. You're doing sine divided by cosine, which means you're flipping. Did you say 1 over 3? Because that's what I heard. Oh, okay. You're looking at me like, I know I did it right. Yeah, that would be correct. All right, next row goes to Joey. Can you tell me the cofunction for the sine of 90 minus theta? It is the cosine of theta. Good. And then, Joey, can you tell me the cofunction cosine of 90 minus theta, what that's equal to? Yeah, sine of theta. All right, Richard, can you tell me about tan and cotan? Cofunction identity?
Tan cotan equals theta. I'm not really sure how to word this because I wasn't understanding it last time.
How do you read that?
That's
Tangent? It's not tan. This is just like saying the tangent of an angle. So tangent of 90 minus theta is what we're doing there. Notice in the line above, we had the sine of 90 minus theta. That was actually equal to the cosine of theta. Well, what we were studying yesterday, Richard, since you're seeking clarification on that topic, theta and 90 minus theta, if you put those together, do you know what you get? 90 minus theta plus theta. If you put them together, what do you get? It is. What they're saying here is that these two things that I just highlighted in green have to add up to 90. So this could be a 30-degree angle, then this one would have to be 60. If this one's 45, this one has to be 45. If this one is 21, this one has to be, process of elimination, 90 minus 21. Close. Swing and a miss. So yeah, put them together, you get your 90-degree angle. Just pick some numbers. All right. What we're saying here is that cofunctions of complementary angles are actually equal to each other. So now tell me about tangent of 90 minus theta. What's it equal to? What's the cofunction for tangent? Cotangent, good. And then what angle has to go here? Yeah. All right, look across the chart. Yes. All right, Jayla, can you give me the last line? Good. Yeah. Questions about that? All right. So now I need some identities. Adam, what's A plus B times A plus B equal to? Uh-huh. And you would be correct. I'm assuming you got that by FOILing. Is that right, Adam? Yeah. Hey, Mark, do you know another way of writing A squared minus B squared? A minus B times a plus b is actually how you would get a squared minus b squared. That's actually a difference of 2 squares. Then you factor it by doing the square root thing like you said. Then you have to put a plus in one parentheses and a minus in the other. Because when you FOIL, you need the AB's to go away. Yeah. All right. Hey, Jaden. A times quantity of B plus C. Did you come up with a different way of writing that? You could. You could. That's not what I was thinking, but you definitely could. Rachel, you got something else? Yeah, just doing the distributive property also. But you're right, addition's commutative. Sometimes it's just as simple as rearranging the 2 things that are with a plus sign. So I like that you had a different way of thinking about it. All right, so Adam. A to the negative first. So remember, are you allowed to have negative exponents? Does anybody remember this one? Adam. Yeah, upstairs, downstairs rule. If it's negative and on the top, you move it to the bottom. If it's negative on the bottom, you move it to the top. All right. Michael, back to you, bud. What's another way of writing A plus B? Pretend it's 3 and 2. Right. But you can't combine A and B. So let's pretend you can't combine 3 plus 2, which you can. What's another way of writing 3 plus 2? Yeah. So sometimes it's just as simple. This was Jaden's take on the problem too. Sometimes it's just as simple as using the commutative property of addition. Okay. We'll come back to these as we move through the next 2 or 3 days worth of material. Our major goal for today, though, is to just identify the identities that we're going to use in this section. This is a little information overload, so screen shade. So far, the co-function identity seems to be the one we spent the most amount of time on, but there is a couple of more that you're going to be responsible for. You must dedicate these to memory. That's a polite way of saying you have to memorize these. They are the reciprocal identities, quotient identities, and Pythagorean identities. The toughest to remember are the last ones, the Pythagorean identities. So you just did the co-function identity table in your warm-up today. That one's done. Reciprocal identities table. When we put the sine of theta on the circle and had to write it as opposite over hypotenuse, the opposite side was a y coordinate and the hypotenuse is the radius. So you know that the sine of theta can be defined as y over r. It is also the reciprocal function for cosecant. And some of you displayed an understanding of that on your homework last night. So you could also write it as the reciprocal of cosecant. We write that as just 1 over the cosecant of theta. If you want to define the cosecant of theta, that's just the reciprocal of sine. So you have r over y instead of y over r. And then you have 1 over the sine of theta in addition. Next one, cosine of theta. It's not y over r. Does anybody remember how that goes? It's not y over r. Cosine's associated with which ordered pair? Which part of the ordered pair? You know, Rachel? Yeah, it is x over r. Very good. So cosine is x over r. You could also describe it as the reciprocal of secant. So that's 1 over the secant of theta. And then secant of theta would then be r over x, the reciprocal for cosine. We write that as 1 over cosine theta. And the last one is tangent. That's not y over r or x over r. Does anybody remember how you divide that out? Adam. Close. Y over x, very good. So tangent is y over x. It's also the reciprocal of cotangent, so you just write that as 1 over cotangent theta. cotangent of theta, that's just x over y, or the reciprocal of tangent. But in symbols, the reciprocal of tangent is just written as 1 over the tangent of theta. All right. So we did cofunctions. We just did reciprocal identities. Now you have quotient identities. And you actually have already used these just a little bit. Again, too much information. In the above chart, you said tangent was y over x, and cotangent was x over y. Well, if you come to understand y as your sine value and x as your cosine value, you could also then write tangent as just sine divided by cosine. It then follows by our reciprocal identity that if you've come to understand cotangent as x over y, and then x is cosine and y is sine, you could actually write cotangent of theta as cosine over sine. Okay. And then lastly, we have three. Woo, what's up? Sure. Whoa. Real sensitive today. Did you have a question about part of it, or? Any other questions so far? Okay, and then the last set of identities we have are your Pythagorean identities. The first one is probably the most important one. I call it like the grand poobah of the Pythagorean identities. You could probably guess that they come from the Pythagorean theorem. I'm going to show you where they come from today. Not that you necessarily have to reproduce today's lesson to kind of show where they come from, but I'm going to show it to you so it makes a little more sense. Let me pause while you're copying. Okay. The first thing I wanted to show you is where on earth did these Pythagorean identities come from? So as an example, again, your homework tonight, by the way, isn't to do identity problems. We're not quite there yet. Your assignment for tonight is to memorize the identity charts, the ones that are in your notes. And I'm going to give you a quiz on these for tomorrow. That's your homework to study for your quiz. I'll show you what the quiz looks like before you leave me today. Now, honestly, memorizing the identities is difficult. So if you can kind of follow where they come from, it does make memorizing them a little bit easier. So in example 1 here, you have to show how sine squared theta plus cosine squared theta equals 1 is derived from the Pythagorean theorem. So it's not like this came from nowhere. It came from the Pythagorean theorem. Can anybody tell me what the Pythagorean theorem is? Go, Joey. Yes, a squared plus b squared equals c squared. And you might recall that, that's a very condensed version of saying the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse for your right triangle. So ultimately, what picture do you have in your head for the Pythagorean theorem? You're thinking about a right triangle where A was one of your legs, B was one of your legs, and then C is your hypotenuse. Now, we've been studying kind of all along how this right triangle is being shoved into the unit circle. And that's how we can get, sort of our information out of this. So I'm going to kind of draw a circle around this, hopefully hitting all the stuff I need to. That's my attempt at a circle from my smartboard here. It's not very nice. What I notice now is that my right triangle hits a point on the circle. That point on the circle is right here. Call it point P. And to get to that point P, I traveled across a distance of A and up a distance of B to get there. By the way, this is supposed to be the unit circle, despite the fact that I kind of swung and missed on the smartboard here a little bit. Can anybody tell me the numeric value associated with C, if this is the unit circle? What is C equal to? Michael, 1. Yes, very good. It is the unit circle because it has a radius of 1. So we now have a value associated with c squared. We know that a squared plus b squared, if it equals c squared, that's like 1 squared, or 1. So already we start to see the Pythagorean identity coming out of this thing. Now, honest to goodness, you could take really any integer you want and put it over 1, right? So you could actually think of a squared as a squared over 1. B squared is b squared over 1 if you want to. What's interesting about this is that, you know, by my quotient property for exponents, I could actually sort of rewrite this next line down as a over 1 squared plus b over 1 squared, and it's still equal to 1. We're going to break these two pieces apart. Watch this. See this a over 1 right here? For my angle theta, look what I have if I do a over 1. I have my adjacent side over my hypotenuse. So what I actually have when I have a over 1 sitting there, I have adjacent over hypotenuse squared. Now, these should be like little implies. Sorry, little arrows there. And then we're going to do it again for b over 1. See that b over 1 right there? If I do b over 1 within relationship to theta, I'm talking about opposite over hypotenuse squared. Still equal to 1 on the right side. Can anybody tell me what adjacent over hypotenuse is? Cosine. And it was squared, theta. Opposite over hypotenuse, what's that? Sine squared theta. And then this is still equal to 1. So it's in this fashion. If we take our Pythagorean theorem, put it inside of the unit circle, you actually do get this first Pythagorean identity. Now, in your notes, it was written to go back to what Jaden was talking about earlier and how what Michael was talking about earlier. Addition is commutative. So it doesn't look exactly like the identity yet, does it? That's because we wrote the identity using our associative property, commutative property of addition. We could write it as sine squared theta plus cosine squared theta equals 1. Yeah, just to make it match, make it official. So that's how the Pythagorean identity, the first one, comes from the original Pythagorean theorem. Did you follow that? If you did, that's good. You're getting ready to take a college level math class, so that's good. They do a lot of that stuff. All right, next up. Now what we're going to do is we're going to use that identity to show you where the other two came from. Ooh, what's up, Adam? Go ahead. Well, sine squared is sine times sine of the angle. Okay, so sine of an angle is a ratio of an opposite side to the hypotenuse. So if I ask you for the sine of 30 degrees, that's a half. So sine squared 30 would be what? Yeah, perfect. Make sense? It's they put the squared in a weird spot, huh? Is that what's throwing you? Yeah. It's the same as taking the sine of theta times itself. Okay. All right, so yeah, now I did want to take just a minute to show you where the other two identities come from. Again, this isn't something you'd have to produce right away. Hopefully by the end of the day tomorrow, you'd be able to replicate what I'm about to do. And I think I'm going to do part A, and I'll see if you can do part B. So what we're going to do is we're going to start, it says, use sine squared theta plus cosine squared theta to show that 1 plus tangent squared theta equals secant squared theta. Okay, and here's what I'm going to go ahead and do. I need to think about tangent squared theta. And in a way, I could rewrite that. Because my mission is to show that this thing actually relates back to sine squared theta plus cosine squared theta equals 1. And by my quotient identity, what I'm coming to understand is that the tangent squared theta is the same as sine squared theta over cosine squared theta. And I'm going to jump back a couple slides to show you where that comes from. I have my identities memorized. You eventually will, too. So notice here I turned tangent into sine over cosine. So back to what Adam was saying, tangent squared theta would then be sine squared theta over cosine squared theta. So right now, I know my identities. You would eventually get there. So tangent squared theta is sine squared theta over cosine squared theta. I also know, based on what we kind of just did in the previous slide also, secant squared theta, that's just the reciprocal identity for cosine, right? So this is the same thing as 1 over cosine squared theta. And now I look at 1. And I'm like, oh, well, 1. Oops. This. No, it's not going to let me do it. Give me a little more space. This 1 right here, I could actually think about that as cosine squared theta over itself. And if you'll notice, basically all I've done is I've divided both sides of the equation by cosine squared theta, which essentially means it's like I never did it. So what I have right now is cosine squared theta plus sine squared theta equals 1, which is the identity I was trying to get back to in the beginning of the problem. Again, addition is commutative, so if you wrote it this way or the other way, doesn't matter to me. Okay. All right, now you're going to try to do the same thing with part B. You need to relate this Pythagorean identity back to the grand poobah, I say, of Pythagorean identities. I want you to take a minute to see if you could relate 1 plus cotangent squared theta equals cosecant squared theta back to sine squared theta plus cosine squared theta equals 1. So you try to do what I do. Good. So I was just going to go over it with you real quick. You did a nice job. What I see people doing is using their quotient identity for cotangent to get started. So our quotient identity for cotangent is cosine squared theta over sine squared theta. Our reciprocal identity for cosecant is 1 over sine squared theta. And then if you want to write 1 so that it has sine squared theta on the bottom, well, you need the sine squared theta on the top. And you'll see that we basically divided the entire problem by sine squared theta. By our division property of equality, that kind of means it never happened. So what you actually end up getting is sine squared theta plus cosine squared theta equals 1 in using your identity. So that looks really, really good. Okay, what I just gave you right now was a copy of your quiz for tomorrow. Do you see that? I gave it to you. Because I want you to practice for your homework tonight. This is what your quiz is going to look like tomorrow, except you can't use this. Okay? You're going to get the same thing tomorrow. I just need you to practice memorizing with this. So if I were you, what I would do is I would try to do it without peeking at my notes. And then I would go back, look at my notes, check my practice quiz, and then anything that you were missing, study that. The trick for the Pythagorean identities, honestly, because they are a little bit tricky, I would just write them out each like 5 times, and they usually stick. So just take a couple minutes, write them out a couple times, make it what they call it kinesthetic memory, like motor memory. Your hand just kind of knows what to do, even if your brain doesn't. Get it to be at that point. What's up, Joey?